start the recording. Okay, so I'm gonna go ahead and go through the concepts for this week. So the chapter that we're going over now is all about potential energy, and the conservation of potential energy as it relates to, or rather the conservation of energy relating potential energy to kinetic energy. The first problem is just a concept problem. Excuse me. You're given a series of works and energies for this like weird setup, this weird rod cylinder sort of setup. And so you're going to do some work on the system. Um, just do like the work done for my problem. And I'm not sure, since this is a concept problem, if everyone will have different numbers, the same numbers. Anyway, so my work done on the system is 200 joules. And then they give us a series of sort of like internal works. So they say if there's a work done by the system on the block, and they tell us that that is, where did that go, 60 joules. And then they say that the kinetic energy increases. So there's a delta K of 130 joules. And then they say that the gravitational potential energy decreases by 20. So delta U is minus 20 joules. And the problem asks us what the thermal energy is, the change in the thermal energy. Just to sort of define that concept, the thermal energy is just the heat. And the idea here is that if I put 200 joules of energy into the system by doing work on it, then whatever doesn't go into the work on the block, the change in kinetic energy, change in potential energy, whatever, however much of that 200 joules doesn't go into each of those processes, will be converted into heat within the system. This isn't like a core concept necessarily. Every now and then you just come across a problem where they ask you about thermal energy, and it's usually just a difference between work done and change in energy. It is related to friction, and it's a work in a way that is done by friction. It's actually energy that is removed by friction or work done by a non-conservative force. This is the only problem that you have on friction in this homework. So that is sort of a blessing, because friction acts a little funky. Anyway, for this problem, as I mentioned, we just look at the total here. So we have 60 plus 130 minus 20. So that would give us 170 joules. And then, as I said, if we need to relate that back to the change in the thermal energy, we just compare these two numbers. I put 200 joules of energy into the system, and 170 joules gets converted to these conservative processes. The difference there will be the amount of heat that is generated within the system. All right. The next problem here is the roller coaster problem. There's actually a few roller coaster problems. Roller coaster problems are like a favorite for potential energy because roller coasters have a height. And so it's just like a common sort of concept that's employed. And there's this drawing where you have like a height h, and then a height h, and then a height h and a half, and then down to the ground, and then you go up. Okay, and your roller coaster starts at this height, and it's going to have some initial velocity. And then we have different points on this path. We have point A at the top of the second peak, and then we have a point B, and we have a point C down here near the ground. And this is a height h initially. Point A is at that same height h. Point B is at h over 2. And then, of course, C is down at the ground. So in other words, that would be a position of 0. Okay, so we're going to employ conservation of energy. And the way that conservation of energy works is it just says that your energy at one point for the roller coaster will be equal to the energy at another point for the roller coaster. So we'll go ahead and call this initial position like the initial. So you could say, for instance, that the energy initial would be equal to the energy at, say, point A. What kind of energy do we have? If you have speed, you have kinetic energy. If you have height, then you have potential energy. And now, of course, you could always sort of define a problem so that you have height. It'll usually be pretty clear. They'll pretty explicitly say, like, you're this certain height off the ground. Another way of sort of phrasing that, though, is to say, if you have some height that you could lose, then you have gravitational potential energy. Okay, so that's one form of potential energy. The other one that we'll see in a few problems is spring potential energy. If the spring is compressed, then you have a spring potential energy. All right, so initially, when our car is up here, as I said, we have a kinetic energy initial, and we have a potential energy due to gravity initial. At point A, we also have a kinetic energy, so the kinetic energy at A, and there's a potential energy due to gravity at A. Now, from here, we just need to plug in our expressions, and we've done these enough, but just to recap, in case your brains are fried from that exam, kinetic energy is a half mv squared, potential energy due to gravity is mg times y, the height. So mg, the force of gravity, times y, the height. That comes from technically integrating mg with respect to height. That's from the definition of work as the integral of force. Anyway, don't need to do the integral, you just need to know mgy. It's a pretty simple calculation, which is nice. And yeah, so I can relate here. I can have my 1/2 mv initial squared plus my mgy at height 0. Well, I know that that height is h, so that would be mgh. And I can relate this to the energies at point A. It'll be 1/2 mv sub a squared plus mgy for the height at A. Well, that height at A is actually the same h. So looking at this equation, we have mgh on both sides. There's the same m, same g, same h. So those will cancel out. And then you can see that our half mv squared initial and our half mv at A squared are going to be equal. Cancel out, your half m's, take a square root. Anyway, the point is that you see that the velocity, or the speed, I should say, initially will be equal to the speed at point A. Why does this happen? They're at the same height. So conceptually, you could answer this question immediately by saying, since A is at the same height as the initial position, the speed's not going to change. We can give everyone a second to copy that down, if anyone is copying it down. We could do the basically identical calculation for any of the other points. So the other point that they're going to ask us to do is, for instance, to relate it to point B. At point B, again, we have a half mv initial squared plus mgh. That's just for the initial. That'll always be on the left-hand side. On the right-hand side, you have a half mv sub b squared plus mgy. What is our y at point B? The y at point B is actually h on 2. So here I'm actually going to have to do a little bit more of a calculation than I had to do before. What you'll see is that we have an mgh on the left-hand side, and we have an mgh on 2 on the right-hand side. So if I subtract mgh on 2 from both sides, then I will have half mv initial squared plus 1/2 mgh is equal to 1/2 m times the speed at b squared, mvb squared. And yeah, and then you solve from here. So you'd cancel out your masses. You could also cancel out 1/2 because you now have that factor out in front of everything. And that gives you v initial squared is equal to, or rather, v initial squared plus gh is equal to the speed at b squared. And then from here, you just plug in the values that are given. We're given everything on the left-hand side, and then you take the square root, and that'll give you the speed at b. As a conceptual check to make sure that your answer is kind of in the right range, you could think to yourself, okay, if I have a loss of height, if I'm losing potential energy as I am from up here to to down here, when I lose height there, that is a loss of potential energy that will go into the kinetic energy. And so conceptually, you'd expect that your speed at point B would be higher than it was initially, right? Because you've turned some of your height into speed. You've turned some of your potential energy into kinetic energy. And that is essentially what you'll get here, because you'll have your initial speed here, and then some factor involving the height and the acceleration due to gravity, which will give you a greater speed on the left-hand side. Okay, the last calculation, I believe. They're also going to ask, I should mention, they're going to ask some questions explicitly relating the potential energy, finding the actual value of the potential energy. But one more problem that we wanted, or one more part of this is the other point, our point C. And we are asked to just perform the calculation that we just did one more time for point C. So again, we have a half mv initial squared plus mgh. On the right-hand side, now we have a half mv sub c squared, the speed at c squared, plus mgy for point C. Now, I mentioned that point C is on the ground. I don't believe there are any questions where we will, there's one, I think like problem 7 or something on the homework is a pendulum question where like the ground won't exactly be set equal to 0. But for the most part on this homework, at least as we're starting off, your ground will be taken to be 0. So the mgy, your y at C, will be 0. And I think they may say that explicitly. I don't think they actually, yeah, they don't explicitly say it. But anyway, you're safe to take the lowest point on the path as being equal to 0 anyway, right? And yeah, okay, so that term right there will go away. So that's equal to 0. And then, as we did at the other 2 points, you just solve for your speed at C. Okay, the other 2 parts of this problem are going to ask us to find the gravitational potential energy at points A and B, given that the gravitational potential energy at C is 0. So they're saying that the potential energy at C is equal to 0. What would our potential energy at A or B be? Well, in either case, you're going to have your potential energy on the right-hand side as it just was, as I was doing the calculation for the speed at C. This potential energy will be 0. And our heights are both measured off of C. So we're good to go here as far as doing the calculation. Now, maybe here you'd want to solve for example. I'll just do for B. If I want to find the potential energy for B, that's this guy right here. All I need to do is just solve this equation just a little bit, just rework it just a little bit. We'll have the potential energy due to gravity at point B, but this would work for any of the points, is equal to the kinetic energy at C minus the kinetic energy at B, which is a half mv c squared plus a half mv b squared. And that would be the calculation. That would give you the energy. The other way, of course, that you could do it is you could just say that your potential energy due to gravity at point B is equal to mgy. This should give you the exact same answer. This is 2 different ways to do it. This one's probably a little bit easier, right? Just make sure that your y is set off of C. But of course, C is equal to 0. So that's quite, easily done there. Okay, we'll come back to the roller coaster problem in a minute. But first, we're going to do the loop-de-loop problem. You'll notice that I give these, I refer to these as if those are the names of the problems. That's because they're very common, and they all make for good quiz questions and good exam questions as well. This loop-de-loop problem is one that we're going to come back to throughout the semester as we build more and more physical understanding, we can apply more and more physical concepts to this problem. Our first take, though, right here is luckily not as difficult as it can get. So it'll get a little more tricky later on the semester. Anyway, we have this block, and the block is at some height h off of the ground, and it's going to go through this loop-de-loop that has, it should be circular. It's circular on your homework. Oop. It has a radius r, that loop-de-loop, and yeah. So we have, I believe we're going to release this guy from rest. You'll have a relationship between the height and the radius. So for me, they tell me that this h is equal to 5 times the radius. It would have to be greater than the radius in order for the block to complete the loop. And so we can, set the ground to be y equals 0, as we always do. Now there's 2 points. There's one point that is on the side of the circle, and the diagram tells us that that is 1 radius. And then there's the other point that you're going to be asked to investigate is at the top of the loop. Right. So in both cases, they're actually just asking about the work done. So I mentioned that we have a relationship between work and potential energy, and I think I covered this a little bit last week, which is a reminder. Work is equal to the negative change in the potential energy, which is the opposite of U final minus U initial, which is just U initial minus U final. If I'm looking for the work done by gravity, then it would be U initial minus U final, which would be mg y initial minus mg y final. And if you'd like, you could factor out your mg, and then you just have y initial minus y final. So this will always be your work done by gravity, provided there isn't, spring or whatever else involved there. Actually, that would still work as a work done by gravity, because we have a force mg, which is not dependent on distance. So the integral will always integrate like this. Okay. Yeah, so in order to solve this problem, for instance, if we want to go from the height, or from the point P up at that height H down to this point Q at the height R, then I would just plug in for this equation for the work done by gravity. It'll just be mg, where you'll have a mass given in the problem. My y initial is up at the height H, which for my problem is defined to be 5r. My y final is just the height of point Q, which is defined to be r, so I just subtract that. And I just happen to get 4 times mgr, just because of what my height was defined to be. Up at the top of the loop, this is the second problem. At the top of the loop up here, what is the height of the block off the ground? In other words, what is your y final going to be? Well, we know that our circle has a radius r. The ground is 1 circle length away. So the height here, I'll write y. Our height here, y, would be equal to twice the radius, or the diameter of the circle. Okay, and then the second part is, the second part, they say set the ground to be 0, so the gravitational potential energy is 0, and they just ask us to find the potential energy at point P and Q and at the top of the loop. And for that, since we're just explicitly asked to find the gravitational potential energy, we would just use this expression. Gravitational potential energy is just equal to mgy, so long as you plug in the correct heights for part C, D, and E, then you'll be able to find the gravitational potential energy there as well. Okay. Problem 4, roller coasters back. I'm actually going to just reuse my diagram. Yeah, my roller coaster diagram here, cool. Okay, so this will be for problem number 4 now. For problem number 4, we go back to the roller coaster problem. It's a little different here as far as like what they're actually asking you to find. Diagram is the same. we still start with some initial speed at the first hill height h, and we're asked to find the speed at points A, B, and C. So again, I believe that is that what we were trying to find in 2. Okay. I already did when I did 2. I was actually solving for the speeds. So that would that this one is actually the one where you solve for the speeds. I should mention then that in problem 2, you're simply looking for the work done by the gravitational force on the car. So as a quick correction, we've already done problem 4. If you want to change that in your notes, for problem 2, you just use that equation that I just had on the last slide. So that work done by gravity is equal to mg y initial minus y final. Oop. Okay. So in that case, we've actually already done problem 4. We've already found our speeds. The part that we haven't done is part D, where they ask how high the car will go on the last hill. So we're going to go up to some height over here, and we're asked to find that height. So this is, again, a max height problem similar to in kinematics. Remember that the maximum height occurs when the speed is equal to 0. So just starting from our initial, we'd have that kinetic energy initial plus the potential energy initial, and that's going to be equal to the kinetic energy, we'll call it final, plus the potential energy final. And yeah, so as I mentioned, our speed is 0 at the maximum height, so your 1/2 mv squared will be 0. And you just have your 1/2 mv initial squared plus your mgh, where h is this height. And that'll just be equal to mg times whatever your y final is. And then you just solve from here, your masses will all cancel out, and you'll solve and get something like y final is equal to v initial squared on 2g plus h, and that's just from isolating y final. Cool, yeah. All right. And my apologies for doing those problems out of order. That's what happens when they reuse that same diagram. All right, problem number 5. Yeah, so in problem number 5, now we're gonna have a spring, and it's a vertical spring. So remember, whenever we have a vertical spring, from last week, we learned that if you have a vertical spring, then you're gonna have not only spring potential energy, but also the gravitational potential energy. Now, initially, they give you the mass of the stone. So for me, they say it's a 7.7 kilogram stone, and they tell you that it's compressed 12 centimeters. If you recall from last week, this is force information that's being given to us. And we can use it to find, because the magnitude of the spring force is equal to k times x, we can use this information, excuse me, this information to solve for k. So the other side of it would be, how do we actually find the force? Well, it'll be equal to the force of gravity, mg. So you'd actually solve this guy right here, and that would give you your spring constant k. Once you have the spring constant k, then we can go into the actual, actually, that's part A, but you need it anyway. Next thing you do is you're going to push the spring down and release it. First thing they ask is, what is the potential energy of the spring when you push it down? For me, it's 28 centimeters. Spring potential energy is 1/2 kx squared. I'll have my k from part A, and then they will give me the compression distance. You simply plug it in here and calculate the spring potential energy. The interesting part is they say, what is the change in the gravitational potential energy? What is the change in the gravitational potential energy? What is the change in the gravitational potential energy? In other words, delta UG question mark. What is the change in the gravitational potential energy when the stone moves from the release point this additional 28 centimeters or additional whatever distance that you compressed it, and it moves from there to its maximum height. Okay, so as we've done previously, we can equate our initial energies to our final energies. What's going on with our initial energy? Initially, the spring is compressed quite a bit, and then sometime later, the spring is stretched out and the block has moved up to some height. We'll have some, technically, we will have some, obviously, we'll have spring potential energy. Should change my color here. In this diagram, and in this situation here, when the spring is compressed, we obviously have some potential energy due to the spring initial. And you could say that we have some gravitational potential energy because it will still ostensibly be some height off the ground. So why not say we have some gravitational initial? And then what about in our final situation? In our final situation, what would our spring potential energy be? Well, since the object is stretched out, let me just double, just a second. I think since our spring is stretched, yeah, so our spring is stretched, which means that we have no spring potential energy. So that's because the spring has released all of its energy, turned it all into gravitational potential energy. So just to make these notes a little comprehensible, I'm going to put there's some, that there could be some spring potential energy final, and then there would also be some gravitational potential energy final. Okay, so let's start there, right? We have spring potential and gravitational potential in both cases. Now, how do these change? Well, the spring final, since our block has been allowed to move to its max height, that final spring potential energy will go to 0. So ultimately, remember, we want to solve for the change in the gravitational potential energy, which is gravitational final minus gravitational initial. So if we want to get a little clever with our algebra here, we could solve this equation for gravitational final minus gravitational initial. You just subtract this term over to the right-hand side. So if I do that, I'll have my potential energy due to the spring initial is equal to potential energy of gravity final minus potential energy of gravity initial. Again, this is just the same as the change in the potential energy due to gravity. And so we know that the change in potential energy due to gravity will just be equal to whatever potential energy you had stored in the spring initially. And again, that's just a half kx squared. And then the last thing you want to do is you want to actually find the maximum height measured from the release point. In that case, what you would do in order to find the actual maximum height, they tell us explicitly, they say if we're measuring off of the release point, right? So this is part D. For part D, you can explicitly set your gravitational potential energy initial equal to 0, because we'll set that to y equal to 0 initially. And so in order to solve for the actual height, we use the relationship that the spring potential initial is equal to the gravitational potential final. That means that a half k x initial squared is equal to mg times y final. And then we go ahead and solve for our height. And that height would be, what's that, k x naught squared on 2mg. That's an m there, 2mg. Yeah, and then that's, that's how you find the height. So all of your energy from the spring has been turned into gravitational potential energy there. All right, let's take a look at concepts for problem number 6. Okay, yeah, cool. So problem number 6 is our pendulum problem. A pendulum is also a common, for whatever reason, it's like this common application of energy. here's why. So you have a pendulum. There's no diagram given this problem, but I'll make my own pendulum. And a pendulum, if anyone is unfamiliar, I guess I could just use this. A pendulum just swings back and forth like this, and there's some height associated with the ends of its motion, and then it swings kind of fast through the bottom. So it's just going to swing like this. Oop, I want to make sure it looks curved. It swings like this from one side to the other, and it makes for a good application of energy because it's going to gain some speed as it swings from the black orientation to the blue orientation here. It's going to have some height that's converted into speed by converting a gravitational potential energy to a speed, or sorry, kinetic energy down at the bottom. And so there's all sorts of questions that sort of relate to these two. The one tricky thing about a pendulum problem is that they're always going to give you like the length of the string and an angle off of the vertical, but they're not going to actually give you the height here. So ultimately, if we want to do any sort of energy calculation, we need to know the difference in the height at like your initial position and your final position. It's not going to be given explicitly, so we have to do just a little bit of geometry in order to solve for it. So to create a simplified geometric picture of what's going on here, we have, a sector of a circle technically, and we want to find just this little piece right here. So we can call that piece H, and then what we can do is we can say we know that this length will be a length L. We know that the whole thing here will also be L, but if I just want this leg down to the H, in other words, the projection of this L on the direction of the vertical string, then that means that this length would just be that total L minus H. And of course, we also have the angle theta. How can I relate these all together? Now we have a right triangle here that's defined in terms of L and L minus H. And we know from SOHCAHTOA that the cosine of our angle theta will be equal to the adjacent, which is L minus H, over the hypotenuse, which is L. And so you can, solve here for H. This would give you, let's see, H is going to be equal to, let me make sure I get my signs correct here, L times 1 minus cosine theta. Okay. And I just skipped a few steps there. But the important thing here is that this gives you a way of tying the length of the string and the angle of the string into a height so that you can then do your conservation of energy, which is hopefully pretty straightforward. And we have some practice doing that. All right, so we're given a speed here for part A just to do the actual energy calculation. Let me clear up some space here. They're going to give us, wish I hadn't drawn that in the middle of the thing. Okay. So we have a few different parts. First part is that they give us the speed at the bottom, the lowest point. So we'll call this, and we can call this point A. Well, yeah, sure, we'll call that point A. And we want to relate it to some other point B and find the speed. So conservation of energy, we know we can relate our energies at point A to our energies at point B. Since A is the lowest point, we can go ahead and set that equal to y equals 0. We can say that there's no gravitational potential energy at point A. In other words, we're treating it as if the pendulum is swinging, and just touching the ground at the bottom. Okay, so at point A then, since we have no height, we have no gravitational potential energy, we're just going to have kinetic energy at point A. And we can relate that to point B. They're going to give us an angle off the vertical, and they're going to ask us what the speed is that is associated with that angle. So at point B, we will also have a kinetic energy. That's how we're going to find the speed at point B. And we will gain some potential energy due to this height h right here. So that will be a potential energy due to gravity at point B. All right, so we can go and plug stuff in here. We have a half mv at a squared is equal to a half mv at b squared, plus we want to do mgy, and our y will be this height right here. So mgl times 1 minus cosine of theta. That's how it'll work. And then from here, you'd cancel out your masses. You'd plug in your speed at A, your length, and your angle, which are all given in the problem. And this would allow you to solve for the speed at B. And I trust everyone can do that calculation. The other thing there, the other problem is that they'll ask us to find the greatest angle with the vertical that the string will make. So what they're asking us for there is they're asking to swing this guy all the way. Oh, is that the only thing I lost? Okay. They're going to say, all right, what if you swing all the way over to some height, and that height would be associated with some other angle. I've already used theta. Maybe I'm going to stick with theta. We'll call this theta final, and we'll associate that, or let's call it theta c. How about that? Theta c, that's associated with some point c. And at point C, so what's going on if we're hitting the maximum angle, that hopefully will sound similar to maximum height. And maximum height we know is related to the point where the speed is 0. So in that case, we'd have our kinetic energy at point A again, it'll be the same. And we'll relate that to at point C, if we have no speed, we have no kinetic energy. So we just have potential energy due to gravity at point C. And then you have 1/2 mv sub a squared is equal to mgy, where y is L times 1 minus cosine of theta. And then you cancel out your masses and solve from there. Last one, they say potential energy is 0 at the lowest point. What is the total mechanical energy of the system? Okay, so I'm not sure that we've actually talked about mechanical energy explicitly yet, but mechanical energy is just the kinetic plus the potential at any given point. So we've kind of implicitly been using mechanical energy. In other words, KB plus UGB is the total mechanical energy. And the mechanical energy is the thing that is conserved, right? You get it. So we can pick any point for part C to solve. Since we're given information about A, my problem solving technique would be to just find the total energy at A. And we already know that that's just a half mv sub a squared. And that's how I would solve there. But of course, the energy has to be the same at every point, unless you have friction, which we've already covered one friction problem that you're responsible for. Okay, problem number 7 is a skier problem, a skier hitting a ramp. Skier comes down a height h, you speed up down the hill, and then hit the ramp. And then the skier will fly through the air. And that path through the air is actually a projectile. So there's actually 2 components to this problem. There's a skier going down the ramp to the jump. That's a height h. That's one conservation of energy. And we call that big H in the problem. And then there's an associated projectile motion problem where the guy goes to a height little h. So go ahead and split this up into 2 problems, part 1 and part 2, when you're doing the calculation. For part 1, we go from a height h down to a height 0, essentially, where you have some speed. So you start with no speed, you end with no height. So you have kinetic initial is equal to potential final, just for the going down the ramps portion. And so you'd have, oh, I flipped those. That should be potential initial is equal to a kinetic final. So yeah, so we just have mg times y, where our y is this big H. That'll be equal to a half mv squared. Cancel your m. You get that v is equal to root 2 gh. It should be make that a little more clearly, a square root 2 gh. So that's how you find your speed. And of course, they're not going to ask us to find the speed explicitly. Instead, what they're going to ask us to do is to find in section 2 what the maximum height is. So they give us an angle for our launch speed. My angle happens to be 20 degrees. And so that would be whatever the speed is that you find at this angle theta. Now, there's one way to do this problem. As I mentioned, this is just a projectile motion problem. So you know how to do this with kinematics. You split up your x and your y. In the y direction, you'd have a final velocity of 0 because you're looking for the maximum height. Your delta y is h, and then you just solve for delta y. There's another way to do this part 2, which I will show you now. And this is actually a conservation of energy. So this is one use for conservation of energy, is that sometimes there are motion problems which could be done a little bit smoother and more quickly with conservation of energy than they would with kinematics. So let's look at, yeah, it's section 2. Let me blow that up just a little bit. So you have some initial speed at an angle theta, and then you're going to fly through the air and come down to the ground. And we want to find, of course, our maximum height. We know from our motion, our 2D motion chapter, we know that our speed can be resolved into an x and y component. So your x component for the speed would be whatever the speed is that you just found times the cosine of theta, and your y component would be the speed times the sine of theta. We know this, we've done this. If I wanted to use conservation of energy, all I need to do is relate the kinetic energy that I have at my initial point to the height or the potential energy that I have at the final point. And I know that this x speed will be maintained throughout the motion. Excuse me. So the only energy that will be transferred into potential energy will be the kinetic energy that is associated with my speed in the y direction. So I can say then that my 1/2 m v sub y squared will be equal to my mg times little h, where little h is the height. Cancel out the masses, and you'll get that your h is equal to the v sub y, which is v sine theta quantity squared over 2g. And this is maybe an equation that you even saw in your, while prepping for the exam. That's a max height equation, which is pretty neat. But yeah, it falls out very quickly from the conservation of energy, so long as you're aware that the y component of the speed is the only thing that's converted into height. Of course, you could still do this problem using kinematics. So if you'd like to do it that way, that's fine too. All right, problem number 8 is another vertical spring. We're dropping a block. The block has a mass. We drop it from a height above the spring, and we want to know the maximum distance that the spring is compressed. So the initial picture looks something like this. We have our spring of constant k. We have our block that is a distance h above the spring. What would our final situation look like if we want to find the maximum distance of the spring compression? That would be some time later, when you'd have a compressed spring with that block sitting on top of it. And that's still your same spring K, obviously. This is your mass M. All right, conservation of energy tells us that my energy in picture A will be equal to my energy in picture B. My total mechanical energy, in other words. I haven't written this part of the equation out. My total mechanical energy at A is equal to my total mechanical energy at B. This is just conservation of energy. The way that we've done this so far is to say, all right, let's add up all of our energies at point A. So at point A, I have a gravitational potential energy that will be released as we move to B, as we decrease our height of our block. So I have potential energy due to gravity at point A. And I do not have a spring potential energy because the block is not in contact. I also don't have a speed because I'm dropping the block. Remember, drop means speed is 0, and thus I have no kinetic energy. I know that in picture B, the block will come to a rest because I'm associating this picture with the maximum compression distance. So it's at rest once more when the spring is fully compressed. So there's no kinetic energy there. We will have lost the gravitational potential energy associated with this height. You'll notice that this is not necessarily just the height h. But since the spring is compressed, we will have a potential energy due to the spring in picture B. So I'll have mg times the y in part A is equal to a half k x sub b squared. Now I mentioned this, but I'm going to go a little bit slower here because this is the difficulty of the problem. Let me just say that is y sub a. Now, there's probably a temptation, and most people, I think, the first time through would say, okay, I have mg y, and I know that my y is the height h, but keep in mind that not only does this block move through that height h, it also moves through the compression distance of the spring. So it's h, and then it's also x final. So in other words, the height that we have in part A, or in picture A, that we do not have in picture B, is h plus x final. So this would be mg h plus x final is equal to 1/2 k, I guess x final we've called xb. So let me just to use the same subscript here. So we have mg h plus xb is equal to 1/2 k xb squared. And as far as solving here, this will be a quadratic since we're solving for x sub b. So you would distribute your mg through the parentheses. You get all your terms on one side, and then you can solve the quadratic however you want to. You can either graph it in your calculator. You can do opposite of b plus or minus square root of b squared minus 4ac all over 2a. Yeah, you do have all the constants that you need. The only trick to this problem is that the height y is h plus x final. And I think you're just solving for, yeah, just compression distance. Okay. Problem number 9. This is another one. This has been a homework problem forever. This problem is a potential energy graph, and it's a little bit of a complicated potential energy graph. But let me see what they give us. Potential energy versus position of a particle with a given mass. And it's traveling along the x-axis. And then they give us all the different potential energies at A, C, D, and particle is released where U forms a potential hill of height U sub B. So, oh man, I guess I'll have to sketch something here. This is what it looks like. You go, dun, dun. I do not like this problem. And then we go way up. Okay. So they tell us that we are released from U sub B with kinetic energy 4. There are two different places where you could have actually there's 3 different places where you could have U sub B. Doesn't really matter which one we use because we know that conservation of energy will give us the same kinetic and potential there. But let's go ahead and say that this is the potential energy associated, that U sub B level. And they tell us that there's a kinetic energy there as well. So we know that we have some energy at point B, and that it would be the potential energy at point B, which is given explicitly, plus the kinetic energy at point B, which is also given explicitly. For me, they say the potential hill is at a height of 12 joules, and the kinetic energy associated with that point is 4 joules. So my total mechanical energy for my system happens to be 16 joules. Yours will be different, but it'll be given to you. Since this isn't the mechanical energy, and since we have a conservative force, this would be the mechanical energy at any other point on the hill. So for one of them, for part A, they ask about the location x equals 3.5 meters, which happens to be at the energy level A. It's, yeah, like this is 3.5 right here. So that happens to be the energy level U sub A. And I know that my energy at A has to be equal to my energy at B. So conservation of energy at B is equal to the energy at A. We know my energy at B is 16. What's my energy at A? It'll be the U at A plus the K at A, potential plus the kinetic. And so I have 16 is equal to, what am I ultimately finding? I'm trying to find the speed. Okay, so I know that U sub A is, for my problem, 9 joules. It's just given in the problem. And then I have plus, whoops, didn't mean to switch colors there, plus 1/2 mv at A squared. 16 minus 9 is 7. And then solve for v sub A. It'll be v sub A is equal to the square root of 2 times 7 will be 14 on m. Yours will be different because you'll have different numbers. But anyway, that's how I trust you can do the algebra here. But that's how you would solve for the speed there. Part B, they just give you another position, 6.5. That would be down here. The potential energy there would be equal to 0 joules. So this calculation is actually a little bit easier. And then they ask for the position of the turning point on the right side and on the left side. So our turning point would be, I'll do the right side, but you could do the left side as well. Our turning point would be wherever, it's going to obviously try to climb the hill, and then it'll hit your maximum height, and then it'll come back down. So the turning point would be wherever your kinetic energy is 0, wherever your speed is 0. In other words, it's just a max height problem. Okay, so in that case, I would set my energy at the right equal to my energy at point B, which we know is 16 joules. Since we have no kinetic energy there, we just have potential energy due to gravity will be equal to the energy at B. And so you have mg times y is equal to the 16 joules. And this will give you that y is equal to 16 on mg. Yours will be different. It's not super important what the 16 is on top there. Now, this will give you a height. Ultimately, you will need to do a little bit of geometry in order to, with the slope of the problem, in order to find where exactly that height is. But you just use the slope of the line and set it and develop sort of a triangle in here, a right triangle using the slope, and find the associated height. And it's going to be some like not nice number. Mine happens to be 7 2/3. But if you do need explicit help with that geometry, feel free to reach out. But we'll go ahead and do the last problem here, problem number 10. Problem number 10. Oh, okay, yes. So this is the friction problem. You're gonna have a horizontal force. You're gonna push a block across a floor. Very like simple setup. The floor has friction, and there's an applied force, and there is a coefficient of kinetic friction. First thing is we're asked to find the work done by the applied force as the block slides through a given displacement. Well, the work done by the applied force we know is just the applied force vector dotted with the displacement vector. Of course, that applied force is in the direction of the displacement vector. So it's just whatever the magnitude of your applied force is times your displacement. Hopefully everybody can do that. Remember, the work done by a specific force is just that force times the displacement. Part B, they ask, during the displacement, what is the thermal energy of the block? Let me just double check. Yeah, okay. During the displacement, the thermal energy of the block increases by a given value. And they ask about the thermal energy of the floor. This is a very weird way of asking this question. I've talked at the beginning about how thermal energy is associated with friction or heat. So the change in the thermal energy in a system, this is, I don't know how they expect anyone to just like sort of intuit this, but they're basically saying that the heat could go into either the block or it could go into the floor, is all they're saying. So you have a change in the thermal energy for the block plus a change in the thermal energy for the floor. It's just a weird way of saying. Essentially, all they're saying is they're asking you to find the change in the thermal energy. So how do we calculate the change in the thermal energy? Well, the change in the thermal energy is just going to be the work done by the force of friction, okay? So this is, you could say, the opposite of the work done by the friction, because the friction will do work and release heat. So that's why there's a negative sign out in front. Now, the work done by friction would be the opposite of the force of friction, dotted with our displacement. And first of all, as far as the dot product goes, our force of friction is always going to be opposing the direction of the displacement. So your friction is to the left, your displacement is to the right. When we take a dot product of those two, it's just their product with a negative sign out in front, right? Because they're in opposite directions, so it'll be negative work. And that's going to cancel out our negative sign out in front. So this is just force of friction times displacement. Now all we need to do is calculate the force of friction. We've done this before. Force of friction is mu times the normal force. And then we have our times d still on the outside. Mu times the normal force. What is our normal force here? They've given us a very, very simple problem. Normal force is straight up. Gravity, or mg, is straight down. Thus, when I sum the forces in the y direction, my normal force is equal to my gravity, right? That's why our applied force is horizontal. So the last thing is you can say that you're changing your thermal energy is mu times mg times the displacement. And yeah, so that's your change in thermal energy. So that would be the quantity on the left side here. They'll give you one of these. I think they give you the thermal energy of the block. So this one is given. You plug in your mu mgd on the left side, and then you just solve for the change in the thermal energy of the floor. Whatever doesn't go in the block has to go into the floor. Yeah, and then the last question asks to what is the increase in the kinetic energy of the block? So we have a work done by the applied force. This is part A. So for my part A, this work ends up being about 130 joules. Oops. This is the work done by the applied force. We also have an increase in thermal energy, or a amount of energy that is dissipated by the friction. So for my problem, this happens to be about 60 joules. So in other words, my applied force puts 130 joules into the system. This goes all the way back to the first problem, the concept problem. My applied force puts 130 joules into the system. 60 of those joules are removed by thermal energy. The remainder then will be the kinetic energy. So the kinetic energy is equal to the work of the applied force minus the change in the thermal energy, which for me is 130 minus 60-ish. And that gives you 70. And then they want us to solve for the associated, oh, that's it, actually, just the increase of the kinetic energy. So it's just the difference between those two, and that just happens to be that 70 joules there. All right, I'll stick around if anyone has any questions. I'll go ahead and stop the recording here.